Now we're going to give you an explicit example for quartz. You're going to need this because you have to do this for your own crystal. So here's our very pretty transparent quartz crystal. And the actual unit cell for quartz has A equal B equal 4.91 angstroms and C equal 5.41. A and B are 90 degrees and gamma is 120. And here are the fractional coordinates. So let's first of all calculate the G matrix. Well, all we need is this for the G matrix. So here we go, and we're going to substitute into the G matrix formula, and here's what our G matrix looks like. So A and B, so it's going to be A dot A is going to be roughly just under 5. You can see A and B are just under 5. So their square is going to be just under 25. You see that comes out. You should always check it out just a little bit, and then you can see C is 5.4, and this is definitely greater than 25 squared, so that looks right too. And then you have A, alpha, and equal beta equals 90 degrees. That gives these these terms, off-diagonal terms, equal to 0 because the cosine of 90 degrees is 0. And then you have the 120, which would be the, over here, would be essentially this squared times a half, which is, you can see that this number here, you're taking minus a half of it, and that comes from this cosine of gamma equal to minus a half. So there you have the G matrix, and the units are angstrom squared. Now let's do this unit cell volume. Well, the volume is just the square root of the determinant of G, which we've just calculated, and that comes out to 113.01 angstrom. You do this on the computer. Then we want the bond angle for SI10, so we're looking at this bond angle, this bond length, first of all. And here's the fractional coordinates. And now we're setting up the length of the vector, and just notice that we have the oxygen is here, and it's minus the silicon, and you have to be really careful to keep that in that same direction. So here's the oxygen minus the silicon over here, and then the oxygen minus the silicon for these two sides are 0. When we go through that calculation, we see that the substitute this value for x up into here, we get our SI10 is 1.6067 angstroms. And now we need to do, since we're looking forward to doing the angle, we have to get this other side, and we go through the same thing, and we notice we get a slightly different number. So these two bonds are not exactly crystallographically the same. They have a little bit of variation, and that's very important in the study of quartz. And finally, we want to get the angle between them, and we substitute these values in, and the computer does it for us, and we get 143.46. And that looks about right. That looks like 143.6. Okay. Now we're going to have another topic. We're going to look at crystallographic directions. They're very important because many phenomena depend on the direction in which you're going in the crystal. So you want to get a crystallographic direction, you want to have two lattice points, and you connect them. And here, we go 2 in A, so this is an ordered pair here. So 2 is the A component is 2, and 1 in B, so we go 2 over in A and 1 up in B. Crystallographic directions are indicated by square brackets. That's extremely important. And another thing is that if you look at this vector here and compare it with this longer vector connecting these two lattice points, the magnitudes will be different, but the direction is the same. So this direction here, this point here would be 4, 2, so you come 4 over and 2 up, but it's the same direction as 2, 1. So we take out any common multiple. In here we get the least common divider, and we get 2, 1 here. We take out the 2 from both of those. So here's the crystallographic direction with our very important square brackets. The direction will always have square brackets, and it'll have an arrow to show which direction it goes. So crystallographic direction connects 2 lattice points. And here's our official definition. Crystallographic direction is a vector between 2 lattice points in which the direction is indicated by u, v, and w in 3 dimensions, where u, v, and w are integers that do not contain a common integer factor except for 1. And the integers u, v, and w are called the indices of the crystallographic directions, and they specify an infinite number of parallel vectors. And here's 3 directions labeled in a crystal. So here you have the red is the 100, and here's the 110, and here is the 111. You can look and see how they form. Now let's have a question. What is this direction over here? Oh yes, it popped up. It's 1, 0, 1, 0, 1 bar, 0 is the red bar in this on the right hand figure. Now let's look at Young's modulus for copper. There's a crystal of copper, and it turns out that along the 110, which is along here, the Young's modulus is 66.7 gigapascals. If you come along the 1, direction, it more than doubles to 130.3 gigapascal. And if you come along the 111, you're going to get an even bigger Young's modulus, 191.1 gigapascals. So if you're doing very careful single crystal work, it really matters what the direction is. Now here's some examples of crystallographic directions which I expect you to be able to do on a quiz. The question to ponder is, the first one is 1 over and 1 up, and it's the 1, 1. Notice the square brackets and notice the arrow. What about this one? You do this one. What is it? Well, you go 2 over and 1 up, so it's square brackets 2, 1. What about this one? Well, you go 1 over in A and nothing in B, so there it is. And in this one, we go minus 1 in A, and we don't go anything in B, so we get minus 1 bar, or 1 bar, 0, square brackets. Now we have, we're going to, in contrast to the directions, we have the crystallographic planes, and they are indicated by the Miller indices. So we have, to get the crystallographic planes and their corresponding Miller indices, we find 2 lattice points and we connect them to form a line. Then we find a third lattice point not on the line, and we define a plane going through these 3 lattice points. This is the lattice plane. So here you have an example of a lattice plane, and it's defined by the 3 lattice points 100, 010, and 001. Now, given one lattice plane, since all lattice points have identical neighborhoods, there's a plane parallel to a given plane passing through every lattice point. So a crystallographic plane is a set of parallel lattice planes. There's an infinite number of these parallel lattice planes, and the Miller indices H, K, and L specify the crystallographic plane. The Miller indices are, by definition, 3 relatively prime integers, H, K, and L, that are reciprocals of the fractional intercepts that the crystallographic plane makes with the crystallographic axis. Well, it's easier to see what's happening than it is to read that definition. So let's compare. We'll be given an example of 2, 1. Now notice we have rounded brackets, not square brackets. So we take the reciprocals of the Miller indices. So the reciprocals of 2, 1 are what? Yes, they're 1/2 and 1/1, which is equal to 1. And then these are the fractional intercepts. So if you look at this red plane, you can see that along the A basis vector, or the x-axis, so to speak, you intercept at 1/2. Along the B, or the y-axis, you intercept at 1, and then you connect these 2 points to give us the plane. The plane is called then the 2, 1 plane. So suppose we want to plot the O1 plane. Now the reciprocal of 0 is infinity, or undefined, and the reciprocal of 1 is 1. So here is your A, and so where does it intercept the A? Well, it doesn't, so it's going to run parallel to A. Where does it intercept B? It's going to go through 0, 1, or it's going to go through 1 along B. So this is the 0, 1 plane. Now, given fractional intercepts, a third and a fifth, how do you get the Miller indices? Well, you take the reciprocals. So the reciprocals of 1/3 and 2/5 are 3 and 5/2. Then you multiply or divide these reciprocals until a set of relatively prime integers are gotten. In this case, you multiply by 2, and the plane is a 6, 5 plane. So here is the 6, 5 plane. Along the x-axis, it comes in at a 6th, and along the y-axis, it comes in at a 5th. The Miller indices are the 3 relatively prime integers, HKL, that are the reciprocals of the fractional intercepts and the crystallographic plane that the crystallographic plane makes with the crystallographic axes. That's the definition. So here are our crystallographic planes. The 100 planes are all parallel to one another. The 111s are all parallel, and here's the 110s. Now let's give us an example. Here's a 2D example of a crystallographic plane. So let's figure out what that plane is. Well, it intersects A at 1, so the reciprocal of 1 is 1. It intersects B at 1, so the reciprocal of B is 1, of 1 is 1, so the plane is the 1, 1 plane. Let's look at this example. We have the A intercept is over here. That's at 1/2. Take the reciprocal of 1/2 and you get 2. B intercepts at 1, so the reciprocal of 1 is 1. So the plane is the 2, 1 plane. And over here you have the red plane is intercepting A at 1, so the reciprocal of 1 is 1. And it's never intercepting B, or if you will, at infinity, then the reciprocal of that is going to be 0. So that plane is going to be the 1, 0 plane. And finally, we have the other side. This red plane intercepts B at 1 and never A, so that's going to be what? The 0, 1 plane. That's exactly right. Now, finally, we're going to look at density. Density is something you've known all your life. And first of all, we need a definition. Z is the number of molecules or formula units per unit cell. For example, hexamethylbenzene has 1 molecule per unit cell, so Z would equal 1 in this case. So the density is often indicated by delta. It's the mass per unit volume. So in the numerator is the mass, so it's the number of this is a molecular level. This is at a atomic or molecular level. This can be either at an atomic or a molecular level. You can have a mass that you can hold in your hand divided by the volume of that mass, or you can go and look at it in terms of the unit cell. If you look at it in terms of the unit cell, you have the Z, which is the number of molecules in the unit cell, and A is the atomic mass of the atom, and here's the atomic mass of the whole formula unit or molecule, and here's the volume of the unit cell, and this is Avogadro's number, or the number of atoms per mole. And here we have written our volume out in terms of the G matrix. So let's look at the density of quartz, and we already have the formula for it. There are 3 SiO2 formula units to the unit cell, so this Z will become a 3 up here when we put it in. And the atomic weight of silicon is 28, oxygen 16, SiO2. You add them up and you get 60.08. And we've already done the G matrix for quartz, and we've found the volume in terms of the G matrix, and we got 113.01, and we want to put it in cubic centimeters because our density is going to be in grams per centimeter. And now we can just put our data into this equation on the top here. The Z is equal to 3. The 60 is the summation of all of the atoms in the unit cell, and then we divide through by the volume, and we want our units to come out at grams per cc, so we need to get rid of the moles and we need to convert this to centimeters. And when you do all this, the density is 2.649 grams per centimeter cubed, and if you didn't have the crystallographic data and you just made a straight measurement, the macro density is 2.660 grams per centimeter cubed. So you can see you get very, very close to the same amount whichever way you do it. Well, that's all for now.